Okay, this is the chapter review for chapter 6 from the Math 2101 book. So hopefully if you're not on that book, this helps you. But if you are on that book, these concepts are important. They are the concepts from the last chapter in the book. So if there's stuff that I'm talking about that you don't understand, then it means you need more time with chapter 6. Okay, I'm going to talk about algebraic modeling. It's the title of the book. What is algebraic modeling? It's one of those titles for a math book that to a student might be unpalatable because it doesn't have any really obvious meaning. What is an algebraic model? Well, I have some examples over here, and these are from higher math. These are types of graph that you don't have to do in this book. But what I'm showing here is a parabola, a special shaped curve that you can get with an equation and put on a graph. This is a straight line with a positive slope. This gets pretty close to what we deal with in this book, Math 2101. Here's a straight line with a negative slope. We don't have to deal with those in this book. And here's a sine wave. This is a really fancy function. All of these, though, can express algebraic models. And what is the model? It's that we can look at a situation and we can try to find math that would explain it. A math equation, for instance, that it approximates the model and would result in the graph that the model seems to be giving us. Then we're able to use the graph, a table of values, and the equation to answer questions about that situation. So what does that mean? We're given some of these clues. Remember the 4 clues. The text that describes the situation, the table of values, the graph, and the equation. We're given some of that, and we're expected to be able to use it to find the rest of that, and then answer questions about the situation. In this course, we deal with 2 types of straight line algebraic models, and I'm showing them both here. This is a partial linear model. It's partial because it doesn't go through the origin. It doesn't go through the point 0, 0 on the graph. And this is a direct linear, which does go through the point 0, 0. We have a lot more of this, but the course does include some of this. The way we're more used to seeing it, though, in this course is that they only show us the top right quadrant, this little section here. So this partial would look something like this, where it's not going through the origin, but it's touching the y-axis, and then it's extending outwards to the right, usually with a positive slope, meaning it's tilted upwards. Or this direct would look something like this. Same thing, except it is actually going through the point 0, 0. So we have to get good at using these models, the partials, and very good at using these direct. Now these direct models happen as a result of a direct proportion. So there you go. That's why we have all this talk about proportions in the earlier chapters of the book. And we practice using them a lot, creating proportions, solving for an unknown in a proportion, knowing the concept of ratio and proportion. All of that becomes very useful as we're doing this type of model. Proportions are also involved in this type of model. It's just that they are not direct proportions. Now the type of equation that goes with each of these. This is y equals kx. There's that letter k, the proportionality constant. We find the proportionality constant and it tells us what number to put in here. K is replaced by a number when we actually are working within a situation. This can also be expressed as y equals ax. It means the same thing, really. It's just that we're using a different letter, a different variable for the proportionality constant. This one has the form y equals ax plus b, where the a is replaced with a number, but so is the b, and that b is what causes this to happen. That b is the y-intercept, which is not equal to 0. So we could write plus b here if we wanted, but the b would be 0, because this one goes through the origin. So we don't bother writing plus 0. But we could write plus 0 if we wanted. That's the only difference between the two. It's not a very big difference, really. Now, we learned a lot of stuff about proportions, and we know that we can, for instance, verify a model like y equals kx with cross multiplication. Let's try that. Let's look at an example of a direct proportional algebraic model situation, and that's what I have right here. I know that I can buy a certain number of pizzas for a pizza party for my classroom. I might buy 1 or 2 or 3 or 4, I haven't decided yet. But I can figure out how much it's going to cost. If I know, for instance, that the pizza always costs $20 per pizza of the size that I'm going to order, then 1 gives us 20, 2 pizzas will cost $40, 3 pizzas cost $60, 4 pizzas cost $80. Okay, let's use cross multiplication to verify this proportionality. Let's say we'll use 2 and 40. 2 pizzas will cost $40. But is that equal to, say, 4 pizzas costing $80? We cross multiply. Bottom times top equals top times bottom. Extremes are multiplied and means are multiplied. Remember that? So we have 40 times 4 equals 2 times 80. 160 equals 160. It verifies, it shows that yes, this is really proportional. And the equation would be y equals 20x. Because the proportionality constant, the a or the k, that we're getting from this is 20. We keep on multiplying the x by 20 to get the y. That's why this works, and we have a verification. So we have an algebraic model, don't we? We have a situation, which I didn't write down, but I said it in words. We have a table of values that goes with the situation. We have a graph, which will look a lot like this, that goes with the situation. We have an equation. We can answer questions. How much would 5 pizzas cost? Sure, we can figure that out in more than one way, with all the things that we have at our fingertips with this model. But I can plug x equals 5 pizzas into this algebraic model, and it'll cost us $100. And that makes sense. Of course, for this all to make sense, we want to define our x and our y. X equals number of pizzas, y equals total cost. There's a model in action. You want to practice with a lot of models that work like this, these y equals kx type of models, because for sure they are important in the exam for this course. They are really the whole point of the Math 2101 book. But in order to be able to do this math, you have to feel comfortable with all the things that were covered in the other chapters. All of that algebra skills from the early chapters, the idea of numerical coefficients, constant terms, being able to move values left and right across an equal sign, the left side of the equation being equal to the right side, all of this stuff that we were talking about as we did those other chapters, it's happening here while we do this math. Then there's this one. Remember this one? It's slightly more complicated because it has the plus b. So what I'll do is I'll just make up a situation right now. There's a bicycle taxi. You get in and you have to pay $5 as soon as you get in, the way taxis usually work. And then you're paying $6 per kilometer. I can turn that into a model, and in fact, it's a necessary skill for this book that I have to be able to take the situation written in text and turn it into this type of model. It's going to be y equals 6x plus 5. The 5 is the $5 I have to pay when I get into the bicycle taxi, and the 6 is the $6 per kilometer. Now I can use the model to answer questions. If I go 4 kilometers, y equals 6 times 4 plus 5, which is 24 plus 5, which is $29. I've answered a question using my model. To do this, again, I'm using all of those algebra skills that were covered so extensively in the early chapters, including this idea about numerical coefficient and constant. The 5 is a constant term. The 6 is a numerical coefficient that's multiplied by this variable. The concept of similar terms. We do not say 6x plus 5 equals 11, because that's wrong. We do not say 6x plus 5 equals 11x. That's wrong. That's mixing apples with oranges. The 6x and the 5 are not similar terms because one of them has the variable and the other one is a constant term. We don't add them. But we can replace the x with a number like we did with this 4, and now we don't have any variables anymore, and we can do our operations following the order of operations, BEDMAS, multiply before add, and we get our answer. So there was a reason for all that stuff to be covered in those earlier chapters. All that I have left to cover in this chapter review is the inverse proportion. Now, inverse proportions exist, and we talked about them a little bit, I think, back in chapter 2, but we can also look at an algebraic model that has an inverse proportion in it. Let's try one. I'm going to erase a little bit of this. I'll erase all of this stuff here, and I'll work with the situation here. Okay, so let's say we decided that 3 pizzas will be enough for the pizza party in the classroom. We paid the $60, we have our 3 pizzas. They happen to be extra large pizzas, so they are cut into 8 slices by the restaurant. So 3 pizzas times 8 slices is 24 slices. We have 24 slices. If 4 people are going to be at the classroom party because everyone stayed home because there was a snowstorm, okay, I made a mistake, so I had to erase them, starting over. All right, we have 24 slices of pizza. If 4 people are going to share them, how many will each person get? I like this pizza thing because students are usually able to calculate it really quick because everyone understands pizza. If there's only 4 people and you have 24 slices, each person is going to get 6. If there are 6 people, each person will get 4. If there are 8 people, each person will get 3. If there are 12 people, each person will get 2. Okay, we have our table of values, and we need an equation to express this. The inverse proportion equation is y equals k over x. Instead of y equals kx, like we had with this one, we have y equals k over x because it's inverse. This is a more means less situation. Remember, more means more and less means less go with direct proportions. More pizzas means more money has to be spent to buy them. Less pizzas means less money is spent. That's direct. But here, more people means less slices per person. As we go up more people, yes, it's less and less slices. Less people means more slices per person. This is a more means less situation, so it is an inverse proportion and it will have this form. It can also be written y equals a over x. We need to define our variables, and I could sort of shortcut and say, look, I already defined them here, but I'll do it the way I like students to do it. X equals number of people, y equals number of slices per person. Finding variables is one of the things that you have to do when you make a model, and it's worth marks. Okay, this will go with either of these forms because they really are the same form. But what is my proportionality constant? What's my k? Well, I can figure that out when I have a table of values by multiplying the x by the y. 4 times 6 equals 24. 6 times 4 equals 24. 8 times 3 equals 24. This keeps working, doesn't it? 12 times 2 equals 24. K is the number you get when you do those multiplications. So the equation is y equals 24 over x. We keep on taking the number of slices, which is 24, dividing it by the number of people, and it tells us how many slices each person will get. Because we built our model with our variables defined that way, and because it's inverse. So we can answer questions with our model, can't we? And of course, there's many ways of answering questions. If 10 people were to eat, how many slices would each person get? I can figure it out the way people usually figure it out when they see the pizza arriving at the door. I can use my model. I can play around with my table of values and look for patterns, but I'm going to use the model. If you have 10 people, y equals 24 divided by 10, which is 2.4 slices per person. So unfortunately, you have to get a knife and start cutting pizza slices into smaller pieces in order to make this happen. But the model works. And it was quite easy with these numbers because we kept on getting whole numbers as our answer. And it's not as easy when you have decimals as answers, but that again is part of the power of the algebraic model. I don't care if I'm going to get a decimal because my model is like a little machine that I can use that keeps on churning out right answers to questions because I carefully built my model following the rules of the inverse proportion. That is what chapter 6 is about. It's about being able to take a situation you're given that might involve an inverse proportion and be able to make a model and answer questions using the model. Or, more often, it will involve a direct proportion and you make a model and you answer questions using that model. That is why the course is called algebraic modeling, because that's what it's teaching us. So, if you understood everything that I was talking about, it means you understand chapter 6. If there are things that you didn't understand, things that you don't feel very strong at being able to do yourself, then that's where it's going to be useful for you to spend a little bit more time with chapter 6.